Lesson 5, we're going to focus on the square root function and the absolute value function. So we've talked a little bit about the square root function already. Example 1, just remember when we see a square root function, there are some key points that we always want to use. So if I make a little quick table of values, remember that I can't take the square root of a negative number. So my values would maybe start at 0. And then I'm choosing some values for x that I can actually find the square root of. So this, if I'm subbing in 0 here, the square root of 0 is 0. The square root of 1 is 1, 2, 3. You might remember that. So this is our parent function for the square root function. This is our root function. We're going to graph it and then state the domain and range. So there is our root function. We haven't talked yet about what the domain and range would be. So this horizontally, if we're thinking of domain, horizontally, this function starts at 0 and it goes to the right forever and ever. So our domain for this one would look like the set of x such that x is greater than or equal to 0. And x is an element of all real numbers, anything from 0 and up. Our range vertically, when we look at this graph vertically, it also started at 0, and it's going to continue slowly, but it's going to continue to go up and up and up, higher and higher forever if we had a big enough piece of graph paper. So we have the set of y such that y is also greater than or equal to 0, and y is an element of all real numbers. So there's our parent function. Now we're going to look at some key points about how to transform this function and how to move it around. So example 2, I'm going to show you the way I do it. I usually use these tables of values. So I might start again with a table of values for my parent function. One thing that I want you to feel like you can do is if you don't like the order of the terms, you can rearrange them. So maybe I'd like my negative x and then the negative 2 next. Something that I really need you to see is that the horizontal translation is always inside a bracket. So you need to be careful, and I'll talk about this again, but I would want to factor out my negative and make this x plus 2. That way I see that there is a reflection in the y-axis because it's inside the square root sign, and I know that I'm actually going to go left 2. So what does this mean? If you're feeling like you are understanding how these graphs look, a reflection in the y-axis would mean that instead of the function starting 0 and going to the right, a reflection in the y-axis, it would start at 0 and go to the left. As well, all of the points have to be moved left 2. So I could imagine this being moved left 2 and this point being moved left 2. And you might be able to just graph that without trying to make a new table. This is just because I feel like this is a foolproof method. If I start with my root function, what I need to do, if I have a reflection in the y-axis, I need to multiply. What do you think? A reflection in the y-axis means it would look like it was over here. So if my x values are positive, now they're negative. For that reflection, I'm going to have to multiply x by negative 1. So all of my x values are going to become negative, although 0 doesn't really change. So this is what it would look like if I reflected it in the y-axis. The next thing, if we want to go left 2, we're going to have to subtract 2 from x. So 0 minus 2 is negative 2, negative 1 minus 2 is negative 3, I'd have negative 6, and I'd have negative 11. My y values, in this case, I'm not translating up or down, so my y values are just going to stay the same. So I know that you probably could have done this without making a table, but this is just a process that we're developing to practice to see if it will make sense to graph some that maybe are more complicated. So this is what our function would look like. And like I said, Up above, you maybe didn't need to make a table. You could have imagined the reflection, and you could have imagined moving all of the points left too. Sometimes if you don't want to do a table, maybe you would just do one thing at a time. You might plot the reflection first and then just slide all of your points over. And then the domain for this function is going to go anywhere to the left as long as it starts, it's anything less than -2. So the set of x such that x is less than or equal to -2, and x is an element of all real numbers. And then the range, again, it looks like 0, anything up from 0. So y such that y is anything greater than or equal to 0, and y is an element of all real numbers. I'll be honest, I think when I see stretches and compressions, that's more often when I'm going to make a nice chart. The first example there that we just did, there weren't any stretches and compressions. I would have felt a little more confident to graph that without making a big chart. So again, if you're not happy with the way this looks, we were able to rewrite this so that it makes more sense to us. For example, the 1/2 could be written out front, and that tells you what your horizontal stretch or compression value is. We can also have x plus 4 written beside it, and just double check yourself. Does that look like it would give you the same thing as up above? I just think this makes more sense to me. I know I'm going to go left 4, but this includes a horizontal stretch by a factor of 2. And you'll see that I start with my parent function again, and these points again, and they'll start to almost become familiar. You'll remember, oh, these are going to be some good key points to use. And because I'm trying to follow BEDMAS, I'm going to definitely look at my horizontal stretch first. So I'm going to have to, it's a horizontal stretch. I need to multiply all of my x's by 2. So 1 times 2 is 2, 4 times 2 is 8, 9 times 2 is 18, but my y values are going to just stay the same for now. Now I'd like to take into consideration moving left 4. So if I'm going to horizontally move left 4, I have to subtract 4 from x. So 0 becomes -4, 2 becomes -2, 8 minus 4 is 4, 18 minus 4 is 14, which probably won't fit on my graph. But if some points don't fit on your graph, I wouldn't worry about them too much. We can still get the idea of what the function looks like. So there's our function. Sometimes you might wonder, which way does the arrow go? Did it start over here and go this way? But this was our first point. That was our starting point, and now it's at -4, 0. So that's where it starts, and it's going to head off this way to the right. So if I'm going to talk about the domain and range for that one, the domain horizontally, this is starting at -4, and it's anything greater than -4. So x is greater than or equal to -4, and x is an element of all real numbers. And the range, again, vertically just looks like y is going to be anything greater than 0. So let's try another one, and we'll see how you feel about this. I know that I'm going to go right 1 and down 3. This is also a reflection in the y-axis, and the 2 means we have a horizontal compression by a factor of 1/2. If it was a vertical stretch of 2, it would be out front. Inside, that's a horizontal compression. So if I start with my parent function, the very first thing I'm going to just focus on would be this -2. And maybe we're getting a little better now, and I might do all of that at once. So what I need to do, if that's a horizontal compression by a factor of 1/2, I have to multiply all my x's by 1/2, -1/2. My y values stayed the same. My x values became negative, and I multiplied all the x values by 1/2. The next thing I want to do, I want to add 1 to my x's, and I want to subtract 3 from my y's. So if you're like me, you'll just do one thing at a time. I'm going to add 1 to all of my x's. So I have to add 1. And then I'm going to take away 3 from all my y's. So -3, -2, -1, and 0. And even though this equation looked fairly complicated, by just breaking it down into steps, we have a new set of ordered pairs that we can graph. And then our domain for this function is the set of x such that x is anything less than, because it's going to the left, less than or equal to 1, and x is an element of all real numbers. And the range for this one is different finally. We're down at -3. Vertically, the lowest point is -3, and it's only going to go up from there. So y such that y is greater than or equal to -3, and y is an element of all real numbers. There's one last thing I just want to mention again. So one thing I'm worried about, if you saw this equation and it looked like that, I would have been, we need to practice the idea that this doesn't just mean that you go left 2. This horizontal translation has to be in a bracket. So you always have to factor out a common factor if it's not written in factored form. So a common factor here would be -2, and I'm left with x minus 1 plus 3. This is the equation that you'd want to work with, not this one up above. Okay, one we haven't talked about much is the absolute value function. So the absolute value function, these bars, maybe you've never even seen those before. All the absolute value symbols mean is that you would take anything that would be inside, like -2, actually is the same thing as 2. So we would treat any value as a positive. So the absolute value signs, that's all they mean. If you had a negative value, the absolute value of a positive is just a positive. But the absolute value of a negative number is positive too. So you can't have any negative values when you're talking about an absolute value sign. We could move the function down. I don't know if you remember, this function looks a little bit like a V. I mean, we could move it lower. But just remember, absolute value, that's the role that those lines play on either side of the x. Usually some of the values we might choose to work with would be -2, -1, 0, 1, 2. When I sub in -2 there, I actually get +2. And if I sub in a -1, I get 1. But 0 is 0, 1, and 2. So how does that look? It's pretty even. We would go -2, 2. -1, 1, 0, 0, 1, 1, and 2, 2. And we could keep going. We could have 3s and 4s, but this is why it looks like a V when we're done. And that's the absolute value function. That is the parent function. The domain is the set of x such that x is an element of all real numbers, because this, just like a parabola, we're going to go all the way to the left and all the way to the right. So the domain is always going to be written that way. The range for an absolute value function, in this case, the set of y such that y is anything greater than 0, because it only is facing up. And y is an element of all real numbers. So now if we perform some transformations on that, here I see one, I recognize it as an absolute value function. It still means I'm going to go right 3. Since this is outside the bracket, this is a vertical stretch by a factor of 2. So there's our key points of our parent function. Then what we notice is that we're always going to do multiplication before we add. So we need a vertical stretch by a factor of 2. So that means if it's a vertical stretch, we're going to have to multiply the y's by 2. So the x values stay the same, but if I multiply all the y's by 2, I would get different values for y. So that has been vertically stretched by a factor of 2. Then I want to think about this final movement. If I'm moving my x to the right, I'm going to have to add 3 to x. So my y's are going to stay the same, but I'm going to have to add 3 to each x value. So I get 1, 2, I'm adding 3, 4, and 5. So now we have our new set of ordered pairs for our function. So the domain of this function is the set of x such that x is an element of all real numbers because it's going to go all the way to the left and all the way to the right. The range vertically is the set of y. In this case, y is just greater than or equal to 0 again, and y is an element of all real numbers. This last one, this is, these are about as complicated as they get. I see that we have a reflection in the x-axis because it's outside. We have a horizontal stretch by a factor of 3. We are going left 2 and up 4. So we have our parent function, our points that we usually use when we're graphing an absolute value function. Because it's inside the brackets, I might start with a horizontal stretch by a factor of 3. So that means we have to multiply our x values, because it's horizontal stretch, our x values by 3. So we'd end up with -6 and -3 and 0 and 3 and 6. But our y values would stay the same. Next thing I would consider is the fact that this is a reflection in the x-axis. So if a point is up here, it becomes down here. So that means the y values actually get multiplied by -1. So all of my y values are going to become negative. And then the last thing that we can do, we usually do both of these steps at once. We're going to subtract 2 from my x's and we're going to add 4 to the y's. So sorry, that's really messy, but I'm going to subtract 2 from all of my x's so you could see that I'm just thinking about doing that one thing first. And then I'm going to add 4 to all of my y's. So it looks like this because it is reflected in the x-axis, so it's sort of flipped upside down, but then it did move up 4 and left 2, so you can kind of see that there's where our starting point was. And then we also have a horizontal stretch. So think of somebody standing at the side of it and pulling the sides of it out and stretching it so it looks really, really wide. Our highest point here is 4. And so when we look at our domain, it's still going to go all the way left and all the way right. So x such that x is an element of all real numbers. And our range is going to be from anything from 4 vertically down.